Welcome back to the Deep Dive. Today we're diving into something, well, a bit mind-bending actually. Have you ever stopped to think why some things in nature just seem inherently handed? You know, like honeysuckle vines always twisting one way, bindweed the other. It's not just a random quirk.
No, not at all. Lewis Carroll even wondered about looking-glass milk in Alice. And Louis Pasteur put it quite bluntly, the universe is dissymmetrical.
Dissymmetrical, okay.
And what's really fascinating is how deep this asymmetry, this chirality runs. It's fundamental to life. You, me, all living things, we're chiral.
How so? Like our hands?
Well, yes, but even internally. Think about organ placement, stomach left, liver right, usually. Even snail shells often spiral one way. It's not just looks, it dictates function.
Okay, I see. And you know, it gets really personal with smells. How can we instantly tell lemons from oranges? Or spearmint from caraway seeds? They seem totally different.
Right, but here's the twist. Chemically, they're almost identical. They're mirror images of the same molecule.
Wait, really? Mirror images?
Exactly. We call them enantiomers. One enantiomer of lemon smells like oranges. Its mirror image smells like lemons. Same molecule, different handedness.
So like R lemon for orange and S lemon for lemon.
Precisely. And carvone is another example, spearmint versus caraway.
But if they're chemically identical, how do our noses know?
That's the key. Enantiomers only behave differently in a chiral environment. And our bodies, our noses, our enzymes are chiral environments. They're designed to interact differently with each hand. Even some bacteria only chew up one specific enantiomer of certain molecules.
Wow, so nature is incredibly specific about making just one hand, which leads to the big question. How do we do that in the lab? Make just one version. And why is it so critical, beyond getting the right scent?
Well, this is where it gets really important. The real-world impact is huge, especially in medicine.
Okay.
Take L-DOPA for Parkinson's. Only
Right.
the L form, the left-handed one, works. The other enantiomer, alpha-DOPA, isn't just useless. It can be toxic. Yeah. Or think about antidepressants like escitalopram. The mirror image just doesn't have the same effect. Sometimes, very rarely, the two hands do different things entirely. One might be a painkiller, the other a cough suppressant.
That's a massive difference. And it's not just drugs, right? You mentioned pheromone.
Absolutely. The Japanese beetle pheromone, Japilure, a classic case. The enantiomer attracts them.
Okay.
But, and here's the kicker, add just 1% of the wrong hand, the S enantiomer, and it completely shuts down the attraction. It acts as an inhibitor.
Wow, just 1%. So controlling this absolute handedness or absolute stereochemistry is vital. Medicine, pest control.
Exactly. And that challenge has driven, well, a huge amount of organic chemistry research for decades. It's not small scale either. Think industrial. By 2007, the company Takasaga was making 1,000 tons of synthetic menthol a year.
1,000 tons. Okay, let's unpack this. Our mission for this deep dive is to explore the strategies chemists use to get this level of control. Where do we start?
We start where nature does. If you want to make just one enantiomer, the basic idea is you need something already chiral, something already handed, to influence the outcome. Right. And nature provides this amazing off-the-shelf collection of enantiomerically pure compounds. We call it the chiral pool.
The chiral pool. Okay, like what?
Amino acids are a prime example. They're the building blocks of proteins, right? Readily available, versatile chemistry, alanine, valine, phenylalanine.
And they naturally come in one dominant handedness.
Yes, mostly the L form, which usually corresponds to S stereochemistry, except for cysteine. Think of them like specialized Lego bricks that already have a fixed, specific shape.
Got it. Pre-handed Legos.
Exactly. And chemists can take these amino acids and chemically modify them, transform them into other useful chiral building blocks.
Like what?
You can reduce them to make chiral amino alcohols, like ephedrine, or you can use a reaction called diazotization to turn them into chiral hydroxy acids.
Hydroxy acids, like lactic acid.
Precisely, like S-lactic acid, or RR plus tartaric acid, which you find in grapes. Crucially, that diazotization process happens with overall retention of the original stereochemistry. It involves two inversions, so it ends up back where it started, configuration-wise.
Two inversions, cancels out. Clever.
And then you have carbohydrates, sugars, widely available too.
Like glucose.
Glucose mannose. Yeah. For example, D-mannose can be converted through a few steps into a protected form of S-glyceraldehyde, another really useful chiral building block.
So how does this play out in a real synthesis?
Well, there's a great example by a chemist named Mori. He synthesized an insect pheromone called ipsinol. He started with S-leucine, straight from the chiral pool.
Okay, an amino acid.
Right. Then, through several steps reduction, adding a protecting group, making an epoxide, reacting it with a Grignard reagent, he carefully transformed it, preserving that initial S-handedness all the way to the final pheromone.
So starting with the right hand lets you build the whole molecule with that same handedness.
Essentially, yes. But there are downsides. Okay.
What are they?
Chiral pool syntheses can sometimes be, well, a bit long-winded. You're kind of forced to work with the specific structures nature gives you.
Shoehorned in.
A bit, yeah. And often, only one enantiomer is cheap and abundant. If you need the other hand, you might be out of luck or it gets very expensive.
Right. So what if the chiral pool doesn't have what you need, or you actually want both enantiomers?
Then we move to our next strategy, actually separating a mixture of the two hands. Resolution.
Resolution. We touched on this before. Remind me how it works.
Okay, so resolution starts with a racemic mixture. That's a 50-50 mix of both left and right-handed molecules. To separate them, you need an enantiomerically pure resolving agent, often something from the chiral pool itself.
So you use one hand to pick out another.
Kind of like that, yeah. Imagine you have a mix of left and right gloves. Your right hand, the resolving agent, can selectively pick out only the right-handed gloves.
Okay, makes sense. How's it done chemically?
Often by forming a temporary chemical bond, usually a salt, between the mixture and the pure resolving agent. A classic example. A Swiss company, Silag, needed one specific enantiomer of an amino acid for a drug. They made the 50-50 mix. Then they added cheap, naturally occurring ephedrine, that's one specific hand of ephedrine. This formed a crystalline salt only with the desired hand of their amino acid.
So one version solidified.
Exactly. The other enantiomers stayed dissolved in the liquid. They just filtered off the crystals, treated them to release the pure amino acid, and boom, separation achieved.
Okay, the pro is it works. What's the con?
The big one is yield. If you only want one enantiomer, the theoretical maximum yield is 50%, right? Because you started with half of what you wanted.
Right, the other half is sort of wasted in that context.
Sort of. But if you actually need both enantiomers, maybe for biological testing to see what each one does, then resolution is perfect because you can usually recover the other one from the leftover solution.
Okay, so chiral pool and resolution are about using or separating what's already there. What about guiding a reaction to make only one hand from the start?
Now we're getting into really clever strategies. This brings us to chiral auxiliaries.
Chiral auxiliaries. Sounds important.
They are. Think of them as temporary handed guides or molecular training wheels that you attach to your starting material.
Yeah.
Once attached, this auxiliary directs any subsequent reaction to happen preferentially on one specific face or side of the molecule. It controls the stereochemistry of the new bonds being formed.
Even though the auxiliary itself isn't part of the final molecule.
Exactly. It does its job guiding the reaction, and then you remove it.
How does the guiding actually work?
Let's take a famous one, the Evans oxazolidinone auxiliary. It's a real workhorse. Imagine you have a flat molecule, maybe with a double bond, that could react from its top face or its bottom face, leading to mirror image products.
Right, a 50-50 mix, usually.
Usually. But when you attach this Evans auxiliary, derived perhaps from an amino acid like valine, it makes the molecule rigid and three-dimensional. Crucially, the auxiliary has bulky groups on it.
Okay.
These bulky groups physically block one face of the reactive part of the molecule, like putting up a shield.
Spheric hindrance.
Precisely.
Yeah.
So the incoming reactant has no choice but to attack from the unshielded face. The result: you form predominantly, often almost exclusively, one specific stereoisomer.
That's really smart. And then you just take the auxiliary off.
Yep. Once the key reaction is done, you cleave off the auxiliary, often in a way that allows you to recover and recycle it, which is great for efficiency and cost.
So it's not separation, it's selective creation. What's the sequence again?
It's basically a three-step strategy. 1, attach your pure handed auxiliary. 2, carry out the reaction, which is now diastereoselective because the auxiliary is directing it. 3, remove the auxiliary to reveal your enantiomerically pure or enriched product.
And you mentioned diastereoselective. That's because the intermediate with the auxiliary isn't an enantiomer, right? It's a diastereomer.
Exactly. The auxiliary makes the two possible products diastereomers, which have different physical properties. We'll come back to why that's super useful. And cleverly, chemists have designed different auxiliaries, maybe derived from the other hand of amino acid, that allow you to access the opposite enantiomer of your product if needed.
Very versatile. How well do they control things?
Extremely well, especially in things like alkylating enolates adding carbon chains. The auxiliary helps form a specific enolate shape, often involving coordination to lithium, making it rigid. Then, a bulky group on the auxiliary, like an isopropyl group, blocks one face, forcing the incoming alkyl group to add to the other side. You can get diastereomeric ratios like 98.2 or even better.
98.2. That sounds very pure. How do chemists talk about that purity?
We use a term called enantiomeric excess, or E, if you have a 98.2 ratio of the desired product to the undesired one. It's there. The excess of the major one is 98 minus 2, which equals 96. So we say it's 96% E. It basically tells you how much more of one hand you have than the other. A 98.2 ratio is also sometimes called an enantiomeric ratio, or ER.
Got it. 96% E. How is that measured accurately? Not just guessing.
Oh, definitely not guessing. Old methods based on optical rotation are often unreliable. Modern chemists use chromatography, specifically HPLC or GC with chiral stationary phases. These columns are designed to interact differently with the two enantiomers, so they separate out and you can measure the amounts.
Like separating the gloves again?
Kind of, yeah. Or we use NMR spectroscopy. You can react the mixture with a pure chiral agent, like Mosher's acyl chloride, to form diastereomers that give different NMR signals. Or use chiral NMR shift reagents that temporarily complex with the enantiomers and make their signals distinguishable.
Okay, sophisticated methods. Now, you mentioned diastereomers being important.
Yes. Here's a huge advantage of auxiliaries. Even if your reaction gives, say, a 94.6 ratio of diastereomers before you remove the auxiliary.
Which is good, but not perfect.
Right. But because these are diastereomers, not enantiomers, they have different solubilities, melting points, etc. So you can often purify the major diastereomer very easily by simple recrystallization. Get it up to 99.1 purity.
Ah, so you purify the intermediate.
Exactly. There was a synthesis of a fragment of a complex molecule called X206, where they went from a 98.2 diastereomeric ratio to 99.1 just by recrystallizing. Then you remove the auxiliary, and you have essentially 100% E product. Purifying diastereomers is way easier than purifying an enantiomer.
That's a huge bonus. And removing the auxiliary, are there standard ways?
Yes, several methods depending on what you want the final functional group to be. You can reduce it off to get an alcohol using LiAlH4 or an aldehyde using dibyl. You can convert it to a weinrebamide to make a ketone later, or use a hydroperoxide anion to get a carboxylic acid. That method is particularly gentle and avoids scrambling the stereocenter.
Lots of options. So summing up auxiliaries, very selective, allows for purification via diastereomers. But downsides?
The main ones are that you need stoichiometric amounts, one auxiliary molecule per starting material molecule, roughly. And you have those extra steps, attach, then remove. They're sometimes called unproductive steps because they add to the atom count temporarily. But despite that, they've been incredibly important. There are others too, like Appulser's camphor-based ones or Meyer's pseudoephedrine auxiliary.
Okay, auxiliaries are powerful, but you hinted there's something even better.
Indeed. We now move to what many consider the pinnacle of achievement in this field, asymmetric catalysis.
Catalysis, meaning small amounts doing a lot of work.
Exactly. Imagine using just a tiny, tiny fraction, maybe 1% or 0.1%, or even less of a chiral catalyst to generate huge quantities of your desired enantiomerically pure product. The catalyst molecule does the job over and over again.
Like a microscopic reusable handed machine.
That's a great way to think about it. And a key transformation here is taking a prochiral ketone, one that could become either hand, and reducing it to a single enantiomer of an alcohol.
How's that done catalytically?
One major breakthrough was the CBS catalyst, named after Corey, Bakshi, and Shibata. It's derived from the amino acid proline linked to boron. You use it in catalytic amounts, maybe 10%.
Okay.
It complexes with borane, the reducing agent, and activates both the borane and the ketone. The key is a highly organized, six-membered ring transition state where the hydrogen is delivered. The larger group on the ketone prefers to sit in a specific position to avoid clashes, which dictates which phase gets reduced.
So the catalyst structure forces the reaction down one path.
Precisely. And even more widely used now are ruthenium-catalyzed reductions, pioneered by Nobel laureate Ryoji Noyori.
Noyori again.
Yes. These use Ru2 complexes with chiral diamine ligands, like something called TSDPEN. Often you need less than 1% catalyst. The mechanism involves the ruthenium complex transferring hydrogen either from H2 gas or another source like isopropanol to the ketone. The chiral ligand creates a specific pocket that forces the ketone to orient itself so the hydrogen adds selectively.
And this works on a large scale.
Oh yes, the company Pliva used a Noyori-type ruthenium catalyst to make kilograms of an intermediate for the asthma drug Montelukast Singulair, achieving 99.8% E. It's incredibly efficient.
Wow. And that work earned Nobel Prizes.
Absolutely. Noyori shared the 2001 Nobel Prize in Chemistry with K. Barry Sharpless and William S. Knowles for their work on chirally catalyzed hydrogenation and oxidation reactions. It fundamentally changed synthetic chemistry.
Okay, hydrogenation, adding hydrogen across double bonds. Can that be done catalytically and asymmetrically?
Yes, another hugely important area. You take an alkene, add H2, and create one or two new chiral centers with specific stereochemistry.
How does that work without just getting a mix?
The key was moving from old-school heterogeneous catalysts like palladium on carbon to soluble metal complexes, usually rhodium or ruthenium, complex with chiral phosphine ligands. These ligands act as the catalyst's hands.
Phosphine ligands, like BINAP. You mentioned that before.
Exactly. BINAP, also developed by Noyori, is a classic example. It's a diphosphine, two phosphorus atoms, and it's chiral itself, not because of a carbon atom, but because rotation around a bond is restricted. It's called an atropisomer.
Atropisomer.
When BINAP wraps around a rhodium or ruthenium atom, it creates a very well-defined chiral environment. It forces the alkene substrate and the hydrogen to come together in only one specific orientation, leading to highly enantioselective hydrogen addition. A crucial point, though. These usually work best when there's a functional group near the double bond that can help coordinate to the metal.
What kinds of molecules are made this way?
A huge range. Knowles at Monsanto developed arch-BINAP catalysis for making an L-DOPA precursor. It's also used for making phenylalanine for the sweetener aspartame. Noyori's RuBiDAP systems broaden the scope, dramatically hydrogenating things like allylic alcohols or unsaturated acids to make S-naproxen, the anti-inflammatory, or R-citronellol for fragrances, often with purity exceeding natural sources.
And the efficiency must be amazing.
Staggering. For making, say, 50 kilograms of product, you might only need 22 grams of the RuBiNAP catalyst complex. Compare that to using stoichiometric auxiliaries. It's far superior for a large-scale synthesis.
Incredible efficiency. Now, Sharpless also shared that Nobel. What was his key contribution?
Sharpless developed several groundbreaking asymmetric reactions. One is the Sharpless asymmetric epoxidation. This targets allylic alcohols next to a double bond and converts the double bond into an epoxide, a three-membered ring with oxygen.
Epoxides are useful building blocks, right?
Very useful. And this reaction is brilliant because it creates two new chiral centers simultaneously and with predictable, controllable stereochemistry. It uses a titanium catalyst, specifically TiOi-PR4, along with diethyl tartrate, or DET, as the chiral ligand.
Tartrate again from grapes.
That's the one. And here's the elegant part. Use L plus DET, the natural form, and the oxygen gets delivered to one face of the double bond, let's say the bottom face. Use DDET, the unnatural mirror image, and the oxygen goes to the top face.
So you choose the product's handedness by choosing the catalyst's handedness.
Exactly. The proposed mechanism involves a dimer of the titanium tartrate complex where the allylic alcohol coordinates, and that specific arrangement directs the oxidant, tert-butyl hydroperoxide usually, to only one face. It's been used industrially to make synthetic disparlor, the gypsy moth pheromone, and in many drug syntheses, like for the beta blocker propranolol.
Very powerful. Are there other epoxidation methods?
Yes, for alkenes that aren't allylic alcohols, especially simple cis-alkanes, there's the Jacobson epoxidation. This uses a manganese catalyst with a different type of chiral ligand called a salin ligand, often using simple bleach as the oxidant. Works very well for specific substrates, like turning indene into its epoxide.
Okay, so epoxidation. What else from Sharpless?
Perhaps his most famous and arguably the best asymmetric reaction is the Sharpless asymmetric dihydroxylation, or AD.
Dihydroxylation, adding two OH groups.
Yes, adding two hydroxyl groups across a double bond, specifically in a syn fashion, meaning both add to the same face. And it does this with incredible enantioselectivity.
How does this one work? Sounds complex.
The recipe is a bit complex, yes. It uses catalytic osmium tetroxide, OSO4, which is constantly reoxidized by a co-oxidant like potassium ferricyanide. There are additives too, but the key ingredients are the chiral ligands. These are based on cinchona alkaloids related to quinine with names like DHQD2-thiacale and DHQ2-thiacale.
Wow, quite the names.
They are, but they work astonishingly well. You can dihydroxylate something like transtilbin and get 99.8% E. They are so reliable they're sold commercially as pre-mixed cocktails. AD mix A and AD mix C, one giving one enantiomer, the other giving the mirror image.
Like the epoxidation, choose your mix, choose your product hand.
Precisely. The idea is that the chiral ligand creates a binding pocket around the osmium, almost like an enzyme active site. The alkene has to fit into this pocket in a specific way before the OH groups are delivered.
And are these diols, the products, useful?
Hugely versatile intermediates. You can do lots with them. For example, convert them into cyclic sulfates. These can then be opened regioselectively by nucleophiles, like a thiazide. Lilly used this to make an intermediate for an anti-HIV drug.
Okay.
Or you can even convert the diol directly into an epoxide, but with retention of stereochemistry, using a clever sequence involving cyclic orthosters. Bristol-Myers Squibb used this to get an epoxide with 98% E starting from the AD reaction.
So many options. Why is this AD reaction considered so good?
A key reason is something called ligand-accelerated catalysis. The chiral ligands don't just provide the chirality. They actually make the reaction go faster than the non-catalyzed or racemic background reaction.
Faster? How does that help?
It means the desired chiral reaction pathway completely dominates. Any slow, non-selective background reaction becomes irrelevant, leading to those incredibly high E values. It's a kinetic effect that ensures purity.
Ligand acceleration. That's fascinating. Can that principle be used to make carbon bonds asymmetrically, building the actual skeleton?
Yes, it can. For reactions that might be sluggish or non-selective on their own, like adding dialkyl zinc reagents to aldehydes, adding a catalytic amount of a chiral amino alcohol can dramatically speed up the chiral pathway. It forms a chiral zinc alkoxide intermediate that directs the alkyl group transfer enantioselectively.
So the catalyst makes the right reaction fast and selective.
Exactly. Similarly, conjugate additions adding carbon groups next to carbonyls can be promoted catalytically and enantioselectively using copper catalysts with chiral phosphine ligands, sometimes derived from BINAP.
This catalytic approach seems incredibly powerful, but it mostly relies on metals, right? Ruthenium, rhodium, titanium, osmium.
Traditionally, yes, but there's been a huge surge, almost a revolution in recent years, focusing on organocatalysis.
Organocatalysis, meaning no metals.
Exactly. Using small, purely organic molecules, often derived from amino acids or other chiral pool sources, as the catalysts themselves.
How does that work?
A great example comes from David McMillan. He showed you can take an unsaturated aldehyde and react it with a chiral secondary amine catalyst often derived from L-phenylalanine. This forms a reactive chiral iminium ion intermediate.
Okay, a charged species.
Right. Now, the catalyst structure is key. It typically has a bulky group, like a phenyl group, positioned strategically. This bulky group acts as a shield, blocking one face of the iminium ion. So when a weak nucleophile comes in, like pyrrole, it's forced to attack from the unshielded backside.
Diastereoselectively again.
Yes. Then the resulting enamine intermediate gets hydrolyzed, releasing the product and, crucially, regenerating the amine catalyst to start another cycle. These catalysts are cleverly designed, often with gem dimethyl groups, to control geometry and prevent side reactions. It's been used in drug synthesis, like for KOX2 inhibitors.
Using just a simple organic molecule derived from an amino acid. That's elegant.
It is, and it brings us back to perhaps the simplest organocatalyst, L-proline itself.
Proline, just the plain amino acid.
Just proline. It was actually discovered way back in 1971, the Hadges-Parrish-Etter-Sauer-Reichert reaction. Quite a mouthful that proline could catalyze the cyclization of certain tritone to form bicyclic ketones with high E.
1971. Why the recent revolution then?
That early work was somewhat niche, but around the year 2000, researchers like Benjamin List and Carlos Barbas realized proline could be used much more broadly, especially for aldol reactions connecting aldehydes and ketones. You can react acetone with an aldehyde using just catalytic proline at room temperature and get like 96% E.
Just proline, how?
The magic seems to be in proline's unique structure. It acts as both an amine, forming an enamine intermediate, and has a carboxylic acid group. This carboxyl group can form hydrogen bonds, organizing the transition state typically a six-membered ring, forcing the aldehyde to approach the enamine from a specific face.
A self-contained organizing principle.
Exactly. It even works for reactions involving hydroxylated ketones, giving specific anti-aldol products. It really bridged the gap between complex metal catalysts and something incredibly simple and biological.
Which as you say, brings us full circle.
Yeah.
From using the chiral pool to using individual amino acids as catalysts. What's the next logical step?
Using nature's actual catalysts.
Yeah.
Enzymes. Biocatalysis.
Using enzymes directly in the lab.
Absolutely. While proline is neat, enzymes are nature's incredibly complex and optimized catalysts. Chemists are increasingly harnessing isolated enzymes for large-scale enantioselective synthesis.
Like what kinds of reactions?
Ketoreductases, often from yeast, are a great example. They can reduce ketones to alcohols with extremely high enantioselectivity, often better than chemical methods, and they can work on non-natural substrates too.
Non-natural.
Yeah, molecules the enzyme would never encounter in the yeast cell, for instance, reducing benzoyl oxyacetone to a chiral alcohol intermediate. This is used industrially, that Montelukast precursor we keep mentioning. It's made on a quarter-ton scale using an engineered ketoreductase.
Wow, so enzymes can be surprisingly versatile or promiscuous, as chemists sometimes say.
They can be, yes. While evolved for specific tasks, many enzymes accept a range of substrates, making them powerful tools for chemists seeking highly pure, enantiomerically enriched molecules.
Okay, so we've covered a lot of ground. From starting with nature's gifts to designing incredibly sophisticated catalysts, both metal-based and purely organic, and even using enzymes themselves. What's the big takeaway here?
The core idea is that asymmetric synthesis is all about mastering the control of absolute stereochemistry, making specifically handed molecules on demand. We've seen the main strategies, using the chiral pool, separating mixtures via resolution, using temporary chiral auxiliaries, and the really powerful approaches of asymmetric catalysis, whether it's with metals, small organic molecules in organocatalysis, or enzymes in biocatalysis.
Right, each with its own pros and cons regarding yield, cost, scale, and what kinds of reactions it's good for.
Exactly. It's a constantly evolving field, always pushing for more efficient, selective, and sustainable ways to make these crucial chiral molecules.
And maybe a final thought for you, our listener, to ponder. As our ability to precisely craft left-handed or right-handed molecules gets better and better, think about the implications. It's obviously huge for medicines safer, more effective drugs. It impacts flavors, fragrances, agriculture. But looking further ahead, how does this mastery of molecular handedness change our ability to truly mimic complex natural processes? Could we potentially even surpass nature in creating the intricate molecular machinery needed for future technologies, advanced materials, maybe even, dare I say it, new forms of synthetic life? Something to think about. Thank you for being part of the Last Minute Lecture family. We'll see you next time.